The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today, more parallel programming, as we will do for the next couple lectures as well. So today we're going to look at how to analyze multi-threaded algorithms. And I'm going to start out with a review of what I hope most of you know from 6006 or 6046, which is how to solve divide and conquer recurrences. Now, we know that we can solve them with recursion trees, and that gets tedious after a while. So I want to go through the so-called master method to begin with, and then we'll get into the content of the course. But it will be very helpful since we're going to do so many divide and conquer recurrences. The difference between these divide and conquer recurrences and the ones for caching is that caching is all tricky by the base condition. Here, all the recurrences are going to be nice and clean, okay, just like you learn in your algorithms class. So we'll start with talking about it, and then we'll go through several examples of analysis of algorithms. And it'll also tell us something about what we need to do to make our code go fast. So the main method we're going to use is called the master method. It's for solving recurrences of the form T of n equals a T of n over b plus f of n. Okay, where we have some technical conditions. A is greater than or equal to 1, b is greater than 1, and f is asymptotically positive. As f gets large, it becomes positive. Okay? When we give a recurrence like this, normally if the base case is order 1, it's convention not to give it, to just assume, yeah, we understand that when n is small enough, the result is constant. Okay? As I say, that's the place where this differs from the way that we solve recurrences for caching, where you have to worry about what is the base case of the recurrence. So the way to solve this is, in fact, the way we've seen before. It's a recursion tree. So we start with T of n, and then we replace T of n by the right-hand side, just by substitution. So what's always going to be in the tree as we develop it is the total amount of work. Okay? So we basically replace it by f of n plus a copies of T of n over b. And then each of those we replace by a copies of T of n over b squared, okay? And so forth, continually replacing until we get down to T of 1. And at the point T of 1, we no longer can substitute here, but we know that T of 1 is order 1, okay? And now what we do is add across the rows. So we get f of n, we get a f of n over b, a squared f of n over b squared, and we keep going to the height of this, which we're dividing by the argument by b each time, so to get down to 1 is just log base b of n. Okay? So the number of leaves is, since this is a regular A-ary tree, is a to the height, which is a to the log base b of n, and for each of those we're paying T of 1, which is order 1. Okay? And so now it turns out there's no closed form solution if I add up all these terms. There's no closed form solution. Okay? But there are 3 common situations that occur in practice. Okay? So yes, this is just n to the log base b of a. Just this term. Okay? Not the sum, just this term. So the 3 cases have to do with comparing the number of leaves, okay, which is times order 1, with f of n. Okay? So the first case is the case where n log base b of a is bigger than f of n. So whenever you're given the recurrence, you compute n to the log base b of a. I hope this is repeat for most people, okay? If not, that's fine, but hopefully it'll get you caught up. N log base b of a, if it's much bigger than f of n, then these terms are geometrically increasing. And since it's geometrically increasing, all that matters is the base case. In fact, actually, it has to be not just greater than, it's got to be greater than by a polynomial amount, by some n to the epsilon amount for some epsilon greater than 0. So it might be n to the 1/2, it might be n to the quarter, it could be n to the 100th. Okay, but what it can't be is like log n, because log n is less than any polynomial amount. Okay, so it's got to exceed it by at least n to the epsilon for some epsilon. In that case, it's geometrically increasing. The answer is just what's at the leaves. So that's case 1, geometrically increasing. Okay, case 2 is when things are actually fairly equal on every level. Okay, and the general cases that we'll look at is when it's arithmetically increasing. Okay, so in particular, where this occurs when f of n is n to the log base b of a times log to some power n for some constant k that's at least 0. Okay, so this is the situation. If k is equal to 0, it just says that f of n, the amount here, is exactly the same as the number of leaves. Okay, in that case, it turns out that every level has almost exactly the same amount. And since they're log n levels, you tack on an extra log n for the solution. In fact, the solution has one more log. Turns out that if it's growing arithmetically with layer, you basically take on one extra log. It's actually like doing the integral of an arithmetic series. If you're adding one, adding the terms of, say, I squared, the result is I cubed. If you have a summation that goes from I equals 1 to n of I squared, the result is proportional to n cubed. And similarly, if it's n to any k, it's I to any k, the result is going to be n to the k plus 1. And that's basically what's going on here. Okay? And then the third case is when it's geometrically decreasing, when the amount at the root dominates. So in this case, if it's much less than n, and specifically its f of n is at least log base is at least n to the epsilon less than n to the log base b of a for some constant epsilon. Okay, it turns out in addition you need f of n to satisfy a regularity condition, but this regularity condition is satisfied by all the normal functions that we're going to come up with. It's not satisfied by things like n to the sine n, okay, which oscillates like crazy. Okay, but it is. It also isn't satisfied by exponentially growing functions, but it is satisfied by anything that's polynomial or polynomial times a logarithm or what have you. Okay, so generally we don't really have to check this too carefully. Okay, and then the answer there is just its order f of n, because it's geometrically decreasing, f of n dominates. Okay, so this review for everybody? Pretty much everybody, yeah. Okay, you can do this in your head. Okay, because we're going to ask you to do this in your head during the lecture. Okay, so yeah, we're all good. Okay, good. One of the things that students, when they learn this in an algorithms class, don't recognize is that this also tells you where in your program, where in your recursive program, you should bother to try to eke out constant factors. Okay, so if you think about it, for example, in case 3 here, it's geometrically decreasing. Does it make sense to try to optimize the leaves? No, because very little time is spent there. It makes sense to optimize what's going on at the root, okay, and to save anything you can at the root. And sometimes the root in particular has special properties that aren't true of the internal nodes that you can take advantage of, okay, that you may not be able to take advantage of regularly. But since it's going to be dominated by the root, trying to save in the root makes sense. Correspondingly, if we're in case 1, this is a very, okay, in case 1, it's absolutely critical that you coarsen the recursion, because all the work is down at this level. Okay? And so if you want to get additional performance, you want to basically move this up high enough that you can cut off that constant amount and get, factors 2, 3, sometimes more out of your code. Okay? So understanding the structure of the recursion allows you to figure out where it is that you should optimize your code. Of course, with loops, it's much easier. Where do you spend your time with loops to make code go fast? The innermost loop, right? Because that's the one that's executing the most. Okay? The outer loops are not that important. Okay, this is sort of the corresponding thing for recursion. Okay, figure out where the recursion is spending the time. That's where you spend time eking out extra factors. Okay, good. So let's, oh, here's the cheat sheet, okay? So, so if it's n to the log base b of a minus epsilon, the answer is n to the log base b of a. If it's plus epsilon, it's f of n. And if it's n to the log base b of a times a logarithmic factor, where this logarithm has the exponent greater than or equal to 0, you add a 1. Okay? This is not all of the situations. There are situations which don't occur. Okay, quick quiz. Okay? So t of n equals 4t of n over 2 plus n. What's the solution? N squared. Good. Okay? So this is n to the log base b of a is n to the log base 2 of 4, which is n squared. That's much bigger than n. It's bigger by a factor of n. Here the epsilon of 1 would do. So would an epsilon of a half or an epsilon of a quarter, but in particular an epsilon of 1 would do. That's case 1. The n squared dominates, so the answer is n squared. So basic idea is whichever side dominates for case 1 and case 3, that's the one that is the answer. Okay? Here we go. What about this one? Yeah, n squared log n, because the two sides are about the same size. Okay? It's n squared times log to the 0 n, tack on the extra log. Okay? How about this one? N cubed. How about this one? Yeah, the master theorem does not apply to this one. Okay? It looks like it's case 2 with an exponent of minus 1, but that's bogus because the exponent of the log must be greater than or equal to 0. Okay? So instead, this actually has a solution of, so it does not apply, it actually has the solution n squared log n. Okay? But that's not covered by the master theorem. You can have an infinite hierarchy of narrowing in things. So if you don't have a solution to something that looks like a master theorem type of recurrence, what's your best strategy for solving it? What's that? Yeah. So recursion tree can be good, but actually the best is the substitution method. Okay, basically proving it by induction. And the recursion tree can be very, very helpful in giving you a good guess for what you think the answer is. Okay, but the most reliable way to prove any of these things is using substitution method. Okay, good enough. So that was review for, I hope, most people? Yeah, okay, good. Okay, let's talk about parallel programming. We're going to start out with loops. So last time we talked about how the Silk++ runtime system is based on essentially implementing spawns and sinks, okay, using the work stealing algorithm, and we talked about scheduling and so forth, okay? We didn't talk about how loops are implemented, and it turns out that, except to mention that they were implemented with divide and conquer. So here I want to go into the subtleties of loops, because probably most programs that occur in the real world these days are programs where people just simply say, here's a parallel loop, make this a parallel loop. Okay, that's it. Okay, so let's take an example of the in-place matrix transpose. Okay, and where we're basically trying to flip everything along the main diagonal. Okay, I've used this figure before, I think. Okay, so let's just do it not cache efficiently. So the cache efficient algorithm actually parallelizes beautifully also. Okay, but let's not look at the cache efficient version, the divide and conquer version. Let's look at a looping version to understand. And once again here, as I did before, I'm going to make the indices for my implementation run from 0, not 1. Okay? And basically, I have an outer loop that goes from I equals 1 up to n minus 1, and an inner loop that goes from j equals 0 up to I minus 1. And then I do a little swap in there. Okay? And in here, I have the outer loop I've parallelized. The inner loop is running serially. Okay? Yeah, good. So, so let's take a look at analyzing this particular piece of code to understand what's going on. So the way this actually gets implemented is as follows. So here's the code on the left. What actually happens in the Silk++ compiler is it converts it into recursion, divide and conquer recursion. So what it does is it has a range from low to high is sort of the common case. We're going to call it on from 1 to n minus 1 because that's the indexes that I've given to the Silk for loop. And what we do is if I have a region to do divide and conquer on, a set of values for I basically divide that in half. Okay? And then I recursively execute the first half and then the second half and then Silk sync. So the two sides are going off in parallel. And then if I am at the base, then I go through the inner loop and do the swap of the values in the inner loop. Okay? So the outer loop is the one that's the parallel loop. That one is we're doing divide and conquer on. Okay? So we basically recursively spawn the first half, execute the second, and then each of those does the same thing. Recursively does the same thing down to n equals, until all the iterations have been done. So any question about how that operates? Okay? So this is the way all the parallel loops are done, is basically this strategy. Now here I mentioned that this is, in fact, what happens is this test here is actually coarsened. Okay? So we don't want to go all the way to n equals 1 because then we'll have this recursion call overhead every time we do a call. So in fact, what happens is you go down to some grain size, okay, of some number of iterations, and at that number of iterations, it then just runs through it as an ordinary serial for loop, okay, in order not to pay the function call overhead all the way down. We're going to look exactly at that issue. Okay, so if I take a look at it from using the DAG model that I introduced last time, remember that the rectangles here are kind of count as activation frames, okay, of the stack frames on the call stack. And the circles here are strands, which are serial sequences of serial code. And so what's happening here is essentially I'm running the code that divides it into two parts, and I spawn one part, then this guy spawns the other and waits for the return, and then these guys come back. And then I keep doing that recursively, and then when I get to the bottom, I then run through the innermost loop, which starts out with just one element to do, 2, 3, and so the number of elements, for example, in this case where I've done 8, I go through 8 elements at the bottom here if this were an 8x8 matrix that I was transposing. Okay? So there's more work in these guys than there is over here. Right? So it's not something that you just can map onto processors in some naive fashion. Okay, it does take some load balancing to parallelize this loop. Any questions about what's going on here? Yeah?
Sorry, why is it that it's 1, 2, 3, 4 up to 8?
Because look, take a look. The inner loop goes from j to I. Right? So this guy just does one iteration of the inner loop. This guy does 2. This guy does 3, all the way up to this guy doing 8 iterations if it were an 8x8 matrix. Okay? And in general, if it's n by n, it's going from 1 to n work up here, but only 1 work down here. Because I'm basically iterating through a triangular iteration space to swap the matrix. So, and this is basically swapping row by row. Okay, questions? Is that good? Everybody see what's going on? So now let's take a look and let's analyze this for work and span. So what is the work of this in terms of n, if I have an n by n matrix? What's the work? The work is the ordinary serial running time, right? It's n squared, good, okay? So basically it's order n squared because these guys are all adding up. This is an arithmetic sequence up to n. And so the total amount in here is order n squared, okay? What about this part up here? How much does that cost us for work? How much is in the control overhead of doing that outer loop? So asymptotically, how much is in here? The total is going to be n squared, that I guarantee you. But what's going on up here? How do I count that up?
Are you assuming that each frame is kind of basically constant time?
Yeah, well in this case it is constant time, right? For these up here, because what am I doing? All I'm doing is that code, the recursion code where I divide the range and then spawn off two things. That takes me only a constant amount of manipulation to be able to do that. So this is all order n. Yeah, this is all order n, total of order n here. And the reason is because in some sense there are n leaves here, and if you have a full binary tree, meaning every child is either a leaf or has two children, then the number of internal nodes of the tree is one less than the number of leaves. Okay? So that's a basic property of trees, that the number of internal nodes here is going to be n minus 1 in this case, right? So we have, in particular, we have 7 here. Okay? Is that good? So this part doesn't contribute significantly to the work. Just this part contributes to the work. Is that good? Okay. What about the span for this? Yeah, what's the span? It's not log n, but your heads are in the right place.
The longest path is going from the root to null.
Yeah, which is the longest path going to be here? Starting here and ending there. Which way do we go? Which way? Down to the right. Down to the right, over, down through this guy. How big is this guy? N. Go back up this way. So how much is in this part going down? And going down and up is log n, but this is n. Good. Okay? So so it's basically order n plus order log n. Order n down here plus order log n up and down, that's order n. Okay, so the parallelism is the ratio of those two things, which is order n. Okay, so that's got good parallelism. Okay, and so if you imagine doing this on a large number of processors, very easy to get sort of your benchmark of maybe 10 times more parallelism than the number of processors that you're running on. Okay, does everybody follow this? Okay, good. So the span of the loop control is order log n. And in general, when you have a for loop with n iterations, the loop control itself is going to have log n is going to have to be added to the span every time you hit a loop. Okay, log of whatever the number of iterations is. Okay? And then we have the maximum span of the body. Well, the worst case for this thing in the body is when it's doing the whole thing. Because whenever we're looking at spans, we're always looking at what's the maximum, okay, of things that are operating in parallel. Everybody good? Questions? Great. Okay, so now let's do something a little more parallel. Okay, let's make both loops be parallel. Okay, so here we have a silk for loop here, and then another silk for loop on the interior. Okay, and let's see what we get here. So what's the work for this? Yeah, n squared, that's not going to change, right? That's not going to change. Okay, what's the span? Yeah, log n, right? So it's log n because the span of the outer control loop is going to add log n. The span of the max span of the inner control loop, well, it's going from log of 1 up to log of I, but the maximum of those is going to be proportional to log n, right? Because it's not regular. There's some. And the span of the body now is going to be order 1. And so we add the logs because those things are in series. Okay, we don't multiply them. Okay? What we're doing is we're looking at what's the worst case. The worst case is I have to do the control for this plus the control for this plus the worst iteration here, which in this case is just order 1. So the total is order log n. Okay? That can be confusing for people, okay, why it is that we add here rather than multiply or do something else. Okay, so let me pause here for some questions if people have questions. Everybody with us? Anybody want a clarification or make a point that would lead to clarification? Okay, yes, question?
If you were to draw a tree like the previous slide, how would it look like?
So yeah, so in fact I had, let's see, I had wanted to do that and it got out of control. So what it would look like is, if we go back to the previous slide, it basically would look like this, except where each one of these guys is replaced by a tree that looks like this with as many leaves as the number here indicates. Okay? So once again, this would be the one with the longest span because this would be log of the largest number. But basically, each one of these would be a tree that looked like that came from this. Is that clear? That's a great question. Anybody else have as illuminating questions as those? Did everybody understand that explanation? What the tree would look like? Okay. Good. Okay? Great. So let's see, how far do we get? There we go. Okay, good. So the parallelism here is n squared over log n. Now it's tempting when you do parallel programming to say, therefore this is better parallel code. Okay? And the reason is, well, it does asymptotically have more parallelism, but generally when you're programming, you're not trying to get the most parallelism. What you're trying to do is get sufficient parallelism. Okay? So if n is sufficiently large, it's going to be way more. If n is 1,000,000, which is typical problem size for a loop, for example, for a big loop, or even if it's a few thousand or whatever, okay, it may be just fine to have parallelism on the order of 1,000, okay, which is what the first one gives you. You know, even if you're so 1,000 iterations is generally a small number of iterations. Okay, so 1,000 by 1,000 matrix is going to generate parallelism of 1,000. Here we're going to get a parallelism of 1,000,000 divided by about 20 log of, or 10 or 20. Okay, so like 100,000. But like, if I'm, you know, if I have 1,000 by 1,000 matrix, you know, that's, you know, the difference between having parallelism of 1,000 and parallelism of 100,000, when I'm running on 100 cores, let's say, it doesn't matter. Up to 100 cores, it doesn't matter. And in fact, running this on 100 cores, that's really a tiny problem compared to the amount of memory you're going to get. Okay, you know, 1,000 by 1,000 matrix is tiny. okay, when it comes to the size of memory that you're going to have access to and so forth. So for big problems and so forth, you really want to look at this and say, okay, but which one is going to have better, of things that have ample parallelism, which ones really are going to give me the best bang for the buck for reasonable machine sizes? Okay, so the goal is not just optimize. That's different from things like work or serial running time. Usually less running time is better. Okay, and it's always better. Okay, but here, parallelism, yes, it's good to minimize your span. Okay, but you don't have to minimize it extremely. You just have to get it small enough. Okay, whereas the work term, that you really want to minimize, because that's what you're going to have to do even in a serial implementation. Question?
So, are you suggesting that the other code was okay?
Well, we're going to look a little bit closer at the issue of overheads. I'm going to do it with a different. So we're now going to take a look at what's the difference between these two codes. Okay, we'll come back to that in a minute. Okay, and the way I want to do it is take a look at the issue of overheads with a simpler example. Okay, where we can see what's really going on. So here, what I've done is I've got a loop that is basically just doing vector addition. Okay, it's adding for I equals 0 to n minus 1, add a of I, add b of I into a of I. Okay, pretty simple code. And we want to make that be a parallel loop. Okay, so I get a recursion tree that looks like this. Okay, where I have constant work in every step there. And of course, the work is order n, because I've got n leaves, and the number of internal nodes, the control is all constant size strands there. So this is all just order n for work. And the span is basically log n, as we've seen, by going down one of these paths, for example. And so the parallelism for this is order n over log n. Okay? So it's a very simple problem. But now let's take a look more closely at the overheads here. So the problem is that this work term contains substantial overhead. In other words, if I really was doing that, if I hadn't coarsened the recursion at all in the implementation of Silk 4, if the developers hadn't done that, then I've got a function call, I've got n function call here for for doing a single addition of values at the leaves. Right? I've got n minus 1 of these guys, that's approximately n. Okay, and I've got n of these guys. And which are bigger, these guys or these guys? Okay, these guys are way bigger. They've got a function call in there. This guy here just has what? One floating point addition. And so if I really was doing my divide and conquer down to a single element, this would be way slower than if on one processor, than if I just ran it with a for loop. So if I do a for loop, it's just going to go through, and the overhead it has is incrementing I and testing for termination. That's it. And of course, that's a predictable branch, because it almost never terminates until it actually terminates. And so that's exactly the sort of thing that's going to have a really, really tight loop with very few instructions. But in the parallel implementation, there's going to be this function call overhead everywhere. Okay? And so therefore, this Silk 4 loop, in principle, would not be as efficient. It actually is, but we're going to explain why it is, what goes on in the runtime system to understand that. So here's the idea, and you can control this with a pragma. So a pragma is a statement to the compiler that gives it a hint. And here this pragma says you can name a grain size and give it a value, g. And what that says is, rather than just doing one element when you get down to the bottom here, do g elements in a for loop when you get down to the bottom. Okay? And that way you halt the recursion earlier. You have fewer of these internal nodes. And if you make the grain size sufficiently large, the cost of the recursion at the top you won't be able to see. Okay? So let's analyze what happens when we do this. So we can understand this by vis-a-vis this equation. So the idea here is if I look at my work, imagine that t iter is the time for an iteration of one iteration of the loop. Basic time for one iteration of the loop. So the amount of work that I have to do is n times the time for the iterations of the loop. And then depending upon my grain size, I've got to do things having to do with the internal nodes. And there's basically going to be n over g of those, okay, times the time for a spawn, okay, which is, I'm saying, is the time to execute one of these things, okay? So if these are batched into groups of g, then they're n over g such leaves. There's a -1 in here, but it doesn't matter. It's basically n over g times the time for a spawn, for time for the internal nodes. So everybody see where I'm getting this? So I'm trying to account for the constants in the implementation. Do people follow where I'm getting this? Ask questions. I see a couple of people who are sort of going, not sure I understand. Okay? Yes? Yeah, so basically the constants are with these t iter and t spawn. Okay, so t spawn is the time to execute all that mess. T iter is the time to execute one iteration here within here. I'm doing, in this case, g of them. So I have n over g leaves, but each one is doing g, so that's n over g times g, which is total of n iterations, which makes sense. I should be doing n iterations if I'm adding two vectors here. So that's accounting for all the work in these guys. Okay? Then, in addition, I've got all of the work for all the spawning, which is n over g times t spawn. Okay? And as I say, you can play with this yourself, play with grain size yourself, by just sticking in different grain size directives. Otherwise, it turns out that the Silk runtime system will pick what it deems to be a good grain size. And it usually does a good job, except sometimes. Okay? And that's why there's a parameter here. Okay? So if there's a parameter there, you can get rid of the that. Yes?
Does the runtime compare, like, is a pragma something that is enforced, or is it something that says, hey?
It's a hint.
It's a hint.
Yes, it's a hint. You know, its compiler could ignore it.
The compiler could ignore it and be like, oh, that's total, like,
yeah.
I have better concept.
Yeah, it should be, it's supposed to be something that gives a hint for performance reasons, but does not affect the correctness of the program. Okay, so the program is going to be doing the same thing regardless. The question is, here's a hint to the compiler and the runtime system. Okay? And so then it's picked at, yeah?
My question is, so there's these cases where you say that the runtime system fails to find appropriate value for that grain size. Like, I mean, basically chooses one that's not as good.
Yes.
If you put a pragma, will the runtime system choose the one that you gave it, or still choose? Like,
No, if you give it, the runtime system will, in the current implementation, it always picks whatever you say is here.
Okay.
And that can be an expression. You can evaluate something there. Okay, it's not just a constant. It could be maximum of this and that times whatever, et cetera. Okay? Is that good? Okay, so this is a description of the work. Now let's get a description with the constants again of the span. Okay? So what is going to be the constants for the span? That's going to be something like, well, I'm executing this part in here now serially. Right? So for the span part, we're basically going to go down on one of these paths and back up. I'm not sure which one, but they're basically all fairly symmetric. But then when I get to the leaf, I'm executing the leaf serially, right? So I'm going to have whatever the cost is, g times the time per iteration, is going to be executed serially, plus now log of n over g. Well, that's the n over g is the number of things I have here, times the cost of the spawn, basically. Okay? Does that make sense? Okay? So the idea is, what do we want to have here if I want a good parallel code? We would like the work to be as small as possible. How do I make the work small? How can I set g to make the work small? Make G, well, make G big or little. If you want this term to be small, you want G to be big, okay? But we also want to have a lot of parallelism, okay? So I want this term to be what? Small, which means I need to make G what? Well, we got an n over G here, but it's in a log, right? It's minus log. So really, to get this small, I want G to be small. So I have tension, trade-off, okay? I have trade-off. So let's analyze this a little bit. So we want essentially, if I look at this, I want G to be bigger. So from this thing, I want G to be, from this one, I want G to be small. But here, what I would like is to make it so that this term dominates this term. Okay? If the first term here dominates the second term, okay, then the work is going to be the same as if I did an ordinary for loop. Okay? To within a few percent. So therefore, I want t spawn over t iter, if I take the ratio of these things, I want G to be bigger than the time to spawn divided by the time to iterate. Okay, and if I get it much bigger than that, then this term will be much bigger than that term, and I don't have to worry about this term. Okay, so I want it to be I want it to be much bigger, but I want it to be as small as possible. Okay, there's no point in making it much bigger than that which causes this term to essentially be wiped out. Okay, did people follow that? Okay. So basically, the idea is we pick a grain size that's large but not too large is what you generally want to do. Okay, so that you have enough parallelism, but you don't. The way that the runtime system does it is it has a somewhat complicated heuristic, but it actually looks to see how many processors you're running on. Okay, and it uses a heuristic that says, let's make sure there's at least parallelism 10 times more than the number of processors. But there's no point in having more iterations than like 500 or something. Okay? Because at 500 iterations, you can't see the spawn overhead regardless. So basically, it uses a formula kind of that nature to pick this automatically. But you're free to pick this yourself. Okay? But you can see the point is that although it's doing divide and conquer, you do this issue of coarsening, and you do want to make sure that that you have enough work to do in any of the leaves of the computation. And as I say, usually it'll guess right. But if you have trouble with that, you have a parameter you can play with. Let's take a look at another implementation just to try to understand this issue. Suppose instead of suppose I'm going to do a vector add. So here I have a vector add of 2 arrays, where I'm basically saying AI gets added into, the value of B added into it. Okay, that's kind of the code we had before. But now what I want to do is I'm going to implement a vector add using silk spawn. Okay? So rather than using a silk for loop, I'm going to parallelize this loop by hand using silk spawn. But what I'm going to do is I'm going to say, for j equals 0 up to, and I'm going to jump by whatever my grain size is here, and spawn off the addition of things of size essentially g, unless I get close to the end of the array. But basically, I'm always spawning off the next g iterations to do that in parallel. Okay? And then I sync all these spawns. Does everybody understand the code? Yeah, I see nods. I want to see everybody nod, actually, when I do this. Otherwise, what happens is I see 3 people nod, and I assume that people are nod. Because if you don't do it, you can shake your head, and I promise none of your friends will see that you're shaking your head. Okay? And since the TAs are doing the grading and they're facing this way, they won't see either. Okay? And so it's perfectly safe to let me know, and that way I can make sure you understand. Okay? So, everybody understand what this does? Okay, so I see a few more. No. Okay. Question. Do we have a question? Or should I just explain again? So this is basically doing a vector add of B into A of n iterations here, okay? And we're going to call it here, when I do a vector add, of basically G iterations. So what it's doing is it's going to take my array of size n, bust it into chunks of size G, and spawn off the first one, spawn off the second one, spawn off the third one, each one to do G iterations. Does that make sense? Okay, we'll see it. So here's sort of the instruction stream for the code here. Okay? So basically it says here's one, we spawn off something of size G. Okay? Then we go on, we spawn off something else of size G, etc. We keep going up there until we hit the silk sink. Does that make sense? Okay, where each of these is doing a vector add of size G using this serial routine. Okay? So let's analyze this to understand the efficiency of this type of looping structure. So let's assume for this analysis that G equals 1 to make it easy, so we don't have to worry about it. So we're simply spawning off one thing here, one iteration here, all the way to the end. Okay? So what is the work for this if I spawn off things of size 1? Asymptotic work. Yeah, it's order n, because I've got n leaves and I've got n guys I'm spawning off, so it's order n. What's the span? Yeah, it's also order n. Okay? Because this is, the critical path goes something like brip, brip, brip. Okay? That's order n length. It's not this, because that's only order 1 length, all those. It's the longest path, okay, is order n. So that says the parallelism is order 1. Okay, conclusion, at least with grain size 1, this is a really bad way to implement a parallel loop. However, I guarantee, and it may not be the people in this room, okay, but some fraction of students in this class will write this rather than doing a silk 4. Bad idea. Okay, bad idea. Generally, bad idea. Okay, question?
Constant factors, not just asymptotic times. Should be something different, right? Because
well, here actually, with grain size 1, this is really bad because I've got this overhead of doing the spawn, and then I'm only doing one iteration. So the ideal thing would be that I really am only paying for the leaves, and the internal nodes I don't have to pay anything for. Yeah, Eric?
Should there be a silk keyword in the VAdd too?
In the where?
In the VAdd?
No, that's serial. That's a
Right,
serial
but
code.
if you're going to call it with silk spawn, don't you have to declare it silk? Not the case?
No.
Never mind.
Okay. Yes, question?
But if G is like 20, then isn't that good enough?
Yeah, so let's take a look. That's actually the next slide. Good. Okay, so go on. So everybody understand. This is basically, this we call puny parallelism. Okay, puny parallelism. We don't like puny parallelism. Okay? We want it, it doesn't have to be spectacular, it has to be good enough. Okay? And this is not good enough for most applications. Okay? Okay, so here's another implementation. Here's another way of doing it. Now let's analyze it where we have control over G. So we'll analyze it in terms of G and then see whether there's a setting for which this makes sense. So if I analyze it in terms of G, now I have to do a little bit more careful analysis here. How much work do I have here if in terms of N and G? Yeah, the work is still asymptotically order N, right? Even if I, because I always have N work in the leaves, even if I do more iterations here, what increasing G does is it shrinks this, right? Shrinks this. Okay. The span for this is what? Yeah, so I heard somebody say it. N over G plus G. Okay? And it corresponds to this path. Okay, so this is the N over G part up here, and this is the plus G. Okay? So what we want to do is to minimize this is we can minimize this. This is its smallest value when these two terms are equal, which you can either know as a basic fact of the summation of these kinds of things, or you can take derivatives and so forth, okay? So this basically, or you can just eyeball it and say, gee, if g is bigger than square root of n, then this is going to be dominant. And if g is smaller than square root of n, then this is going to be dominant. And so when they're equal, that sounds like about when it should be the smallest, which is true, okay? So we pick it to be about square root of n to minimize the span. Okay, since g, I don't have anything to minimize here. So pick it around square root of n, okay? Then the span is around square root of n. And so then the parallelism is order square root of n. Okay, so that's pretty good. So that's not bad. So for something that's a big array, an array of size 1,000,000, parallelism might be 1,000. That might be just hunky-dory. Okay, question? What's that?
Plus g, I don't see where.
We've picked g to be equal to square root of n.
Take out g plus n over g, then plus g, I don't see where.
We don't see where this g came from? Okay, this g comes from because I'm doing g iterations here. So remember that these are now of size g. I'm doing g iterations in each leaf here, if I set g to be large. So I'm doing n over g pieces here plus g iterations in my friend. Is that clear? So the n over g is this part. This size here, this is not 1. This has g iterations in it. So the total span is g plus n over g. Okay? Good. Good. Any other questions about this? So I get order square root of n. Okay? And so this is not necessarily a bad way of doing it. Okay? But the Silk 4 is a far more reliable way of making sure that you get the parallelism than spawning things off one by one. One of the things, by the way, in this I've seen people write code where their first instinct is to write something like this, where this that they're spawning off is only constant time. And they say, gee, I spawned off n things, why didn't it? That's really parallel. Okay? When in fact their parallelism is order 1. Okay? So it's really seductive to think that you can get parallelism by this trait. It's much better to do divide and conquer. And Silk 4 does that for you automatically. Okay? If you're going to do it by hand, sometimes you do want to do it by hand, then you probably want to think more about divide and conquer to generate parallelism because you'll have a small span than doing many things one at a time. Okay, so here's some tips for performance. So you want to minimize the span. So the parallelism is the work over the span. So you want to minimize the span to maximize parallelism. And in general, you should try to generate something like 10 times more parallelism than processors if you want to get near perfect linear speedup. In other words, a parallel slackness of 10 or better is usually adequate. Okay? Usually adequate. Okay? If you can get more, you're now talking that you can get more performance, but now you're likely getting performance increases of 5 or in the range of 5% or so, 5 to 10%, something like that. Okay? Second thing is if you have plenty of parallelism, try to trade some of it off to reduce work overhead. So this is a general case. This is what actually goes on underneath in the Silk++ runtime system is they are trying to do this themselves, but you in your own code can play exactly the same game. Whenever you have a problem and it says, whoa, look at all this parallelism, think about ways that you could reduce the parallelism and get something back in the work term, of the efficiency of the work term. Okay? Because the performance in the end is going to be something like T1 over P plus T infinity. And if T infinity is small, it's like T1 over P, and so anything you save in the T1 term is saving you overall. Okay? It's going to be a savings for you overall. Okay, use divide and conquer recursion on parallel loops rather than spawning one small thing after another. In other words, do this, not this, generally. Okay? And here's some more tips, okay? Another thing that can happen is that we looked at here was make sure that the amount of work you're doing is reasonably large compared to the number of spawns. You can also say this is true when you do recursion for function calls. Make sure if you're just in serial programming, you always want to make sure that the amount of work you're doing is small compared to the number of function calls you're doing, if you can, and that'll make things go faster. Okay, so same thing here. Amount of work should be you want to have a lot of work compared to the total number of spawns that you're doing in your program. Okay? So spawns, by the way, on this system are about 3 or 4 times the cost of a function call. Okay? So they're sort of the same order of magnitude as a function call. Okay? A little bit heavier than a function call. So you can spawn pretty readily. Okay? As long as the total number of spawns you're doing isn't dominating your work. Generally, parallelize outer loops as opposed to inner loops if you're forced to make a choice. Okay, so it's always better to have an outer loop that runs in parallel rather than an inner loop that runs in parallel. Because when you do an inner loop that runs in parallel, you're only getting, you've got a lot of overhead to overcome. But in an outer loop, you've got all of the inner loop to amortize against the cost of the spawns that are being used to parallelize the outer loop. Okay? So you'll do many fewer spawns if you, in the implementation. Okay? Watch out for scheduling overheads. Okay? So if you do something like this, so here we have, we're parallelizing an inner loop, okay, rather than an outer loop. Now, this turns out it doesn't matter which order we're going in or whatever. It's generally not desirable to do this because I'm paying scheduling overhead n times through this loop. Whereas here I pay for scheduling overhead just twice. Okay? So it's generally better if I have n pieces of work to do rather than, in this case, parallelizing. So let me slow down here. So let's look at what this code does. This says go for 2 iterations. Okay? Do something for which is going to take n iterations. Okay? For j. So 2 iterations for I, n iterations for j. It's better to parallelize if you look at the parallelism of this, what is the parallelism of this assuming f is constant time? What's the parallelism of this code? Two. Okay, the parallelism of 2, because I've got 2 things on the outer loop here, and then each is n. So my span is essentially, n. My work is like 2n. Something like that. So it's got a parallelism of about 2. What's the parallelism of this code? What's the parallelism? It's not n, because I'm basically going through this serially, the outer loop serially. What's the theoretical parallelism of this? So for each iteration here, the parallelism is 2. No, it's not n. It can't be n because I'm basically only parallelizing 2 things, and I'm doing them serially, right? The outer loop is going serially through the code, and it's spawning off 2 things, 2 things, 2 things, 2 things, 2 things, and waiting for them to be done. 2 things waiting for it to be done. 2 things waiting for it to be done. Okay? So the parallelism is 2. These have the same parallelism. However, if you run this, this one will give you a speed up of 2 on 2 cores. Very close to it. Because there's the scheduling overhead here, you've only paid once for the scheduling overhead, and then you're doing a whole bunch of stuff. So remember, to schedule it, it's got to be migrated, it's got to be moved to another processor, etc. This one is not even worth probably to steal each of these individual things. You're spawning off things that are so small, this may even have parallelism that's less than 1 in practice. Okay? And if you look at the SilkView tool, this will show you a high burdened parallelism, because the the Silk View tool, the burden parallelism tells you what the overhead is from scheduling, okay, as well as what the actual parallelism is. And it recognizes that, oh, gee whiz, this thing really has very small that there's almost no work in here. So you're trying to parallelize something where the work is so small it's not even worth migrating it to take advantage of it. Okay? So those are some tips. Okay, now let's go through and analyze a bunch of algorithms reasonably quickly. We'll start with matrix multiplication, a problem you have. People seen this problem before? Okay. Okay. Here's the matrix multiplication problem. Okay, and let's assume for simplicity that n is a power of 2. So basically, let's start out with just our looping version. In fact, this isn't even a very good looping version because I've got the order of the loops wrong, I think. But it is just illustrative. So we basically, let's parallelize the outer 2 loops. I can't parallelize the inner loop. Why not? What happens if I tried to parallelize the inner loop with a Silk 4 in this implementation? Why can't I just put a Silk 4 there? Yeah, somebody said it.
Does res in CI shape?
Yeah, we get a race condition. We have more than 2 things in parallel trying to update the same Cij, and we'll have a race condition. Okay? So always run Silk View and to tell your performance, but always, always run Silk Screen to tell whether or not you've got races in your code. Okay? So yeah, you'll have a race condition if you try to naively parallelize the inner loop here. Okay? So let's see. So the work of this is what? Yeah, it's order n cubed. It's just 3 nested loops, each going to n. Okay, what's the span of this? What's the span of this? Yeah, it's order n because it's log for the n for this loop, log n for this loop, plus the maximum of this, well that's n. Log n plus n is order n. Okay? So order n span, which says parallelism is order n squared. Okay? So for 1,000 by 1,000 matrices, the parallelism is on the order of 1,000,000. Wow. Okay, that's great. However, it's on the order of 1,000,000, but as we know, this doesn't use cache very effectively. Okay? So one of the nice things about doing divide and conquer is, as you know, that's a really good way to take advantage of caching. Okay? And this works in parallel too. Okay? And in particular because whenever you have sufficient parallelism, these processors are executing the code just as if they were executing serial code. So you get all the same cache locality you would get in the serial code in the parallel code, except for the times that you're actually migrating work. And if you have sufficient parallelism, that isn't too often. So let's take a look at recursive divide and conquer multiplication. So we're familiar with this too. Okay? So this is 8 multiplications of n over 2 by 2 matrices and 1 addition of n by n matrix. So here's the code. Okay, using a little bit of C++ism. So I've made the type a variable t. So we're going to do matrix multiplication of an array A, the result is going to go in C, and we're going to basically have A and B, and we're going to add the result into C. We have n, which is the side of the submatrix that we're working on, and we're also going to have an int size, which is the length of the row in the original matrix. So remember when we do matrix things, if I take a submatrix, it's not contiguous in memory. So I have to know the row size of the matrix that I'm in order to be able to calculate what the elements are. Okay? So the way it's going to work is I'm going to assign this temporary d, okay, by using the new, which is basically memory allocation C++, array of size n by n. And what we're going to do is then do 4 of the recursive multiplications, these guys here, into the elements of C, and then 4 of them also into D. Okay, and that using the temporary. And then we're going to sync after we get all that parallel work done, and then we're going to add D into C. And then we'll delete D because we allocated it up here. Okay, so everybody understand the code? Okay, so we're doing this, it's just we're going to do it in parallel. Good? Questions? Okay. So, right, so this is the row length of the matrices so that I can do the base case and in particular partition the matrices effectively. I haven't shown that code. Okay, and of course the base case normally would want to coarsen for efficiency. I'd want to go down to something like maybe a 8 by 8 or 16 by 16 matrix, and at that point switch to a something that's going to use the processor pipeline better. The base cases, once again, I want to emphasize this because a couple of people on the quiz misunderstood this. The reason you coarsen has nothing to do with caches. The reason you coarsen is to overcome the overhead of the function calls. And the coarsening is generally chosen independent of what the size of the caches are. It's not a parameter that it has to be tuned to cache size. It's a parameter that has to be tuned to function call versus ALU instructions and what that balance is. Okay? Question?
But don't you also, I mean, I understand that's true, but I thought, I mean, maybe I recall it wrong, but I thought we wanted in general, in terms of caching, that you would choose it somehow so that all of the data that you have would somehow fit or almost.
But that's what the divide and conquer does automatically. The divide and conquer keeps having it until it fits in whatever size cache you have. And in fact, we have 3 caches on the machines we're using.
Yeah, but I'm saying if your course in constant is too big, that's not going to happen.
If the course in constant is too big, that's not going to happen. But generally, the caches are much bigger than what you need to do to amortize the cost. But you're right, that is an assumption. The caches are generally much bigger than the size that you need in order to overcome function call overhead. Function call overhead is not that high. Okay? Good. I'm glad I raised that issue again. Okay? And so we're going to determine the submatrices by index calculation. And then we have to implement this parallel add, and that I'm going to do just with a doubly nested for loop. Okay? To add the things. There's no cache behavior I can really take advantage of here except for spatial locality. There's no temporal locality because I'm just adding 2 matrices once. So there's no real spatial locality temporal locality that I'll get out of it. Okay, and here I've actually done the index calculations by hand. Okay. Okay, so let's analyze this. So to analyze the multiplication program, I have to start by analyzing the addition program. Okay, so this should be, I think, fairly straightforward. What's the work for adding 2 n by n matrices here? N squared, good. Okay, just doubly nested loop. What's the span? Yeah, here it's log n. Very good. Okay, because I've got log n plus order 1. Okay? Good. So I'm not going to analyze the parallelism because I really don't care about the parallelism of the addition. I really care about the parallelism of the matrix multiplication. But we'll plug those values in now. Okay, what is the work of the matrix multiplication? Well, for this, what we want to do is get a recurrence that we can then solve. So what's the recurrence that we want to get for m of 1 of n? Yeah, it's going to be 8 m sub 1 of n over 2 plus, because that corresponds to these things, plus some constant stuff plus the work of the addition. Okay, does that make sense? We analyze the work of the addition. What's the work of the addition? Order n squared. So that's going to dominate that constant there. So we get 8 And what's the solution to this? Okay, back to master theorem. Now we're going to start pulling out the master theorem like multiple times per slide for the rest of the lecture. N cubed, because we have log base 2 of 8, that's n cubed, okay, compared with n squared. Okay, so we get a solution which is n cubed, case 3 of the master theorem. Okay, so that's good. The work we're doing is the same asymptotic work as we're doing for the triply nested loop. Okay, now let's take a look at the span. Okay, so what's the span for this? So once again, we want a recurrence. What's the recurrence look like? So the span of this is going to be the span of, it's going to be the sum of some things. But the key observation is that it's going to be, we want the maximum of these guys. Right? So we're going to basically have the allocation is constant time. We have the maximum of these, which is m of infinity of n over 2, and then we have the span of the add. Okay, so we get this recurrence. Okay, m infinity sub n over 2, because we have only to worry about the worst of these guys. And the worst of them is, they're all symmetric, so it's basically the same. We have a of n, and then there's a constant amount of other overhead here. So any questions about where I pulled that out of? Why that's the recurrence? Okay, so this is the addition, the span of the addition, okay, of this guy that we analyzed already. What is the span of the addition? What did we decide that was? Log n. Right, so basically that dominates the order 1. So we get this term, and what's the solution of this recurrence? What case is this? Yeah, it's log squared n, yep. Okay? So basically it's case 2. So if I do n to the log base b of a, that's n to the log base 2 of 1. Okay, that's just 1. Okay? And so this is basically a logarithmic factor times the 1. So we add an extra log. We get log squared n. Okay? So that's just master theorem plugging in. So here the span is order log squared n. Okay? And so we have the work of n cubed, the span of log squared n. So the parallelism is the ratio, which is n cubed over log squared n. Okay? Not too bad. For 1,000 by 1,000 matrices, the parallelism is about 10 million. Plenty of parallelism. Plenty of parallelism. So let's use the fact that we have plenty of parallelism to say, let's get rid of some of that parallelism and put it back into making our code more efficient. So in particular, this code uses an extra temporary d, which it allocates here and it deletes here. Okay? And generally there's a good rule that says if you use more storage, you're going to use more time, because you're going to have to look at that storage. It's going to take up space in your cache, and is generally going to make you slower. So things that use less storage are generally faster. Okay? Not always the case. Sometimes there's a trade-off, but often it's the case. You use more storage, it runs slower. So let's get rid of this guy. How do we get rid of this guy? Yeah, what's it?
Move all the ones that are probably steam, and then you move out of this no longer span, and no longer slot nodes or above.
You can do those serially, you're saying?
Yeah, you do those serially and just add on.
You do those serially and add. It turns out if you do that, you're going to be in trouble, because you're going to not have very much parallelism, unfortunately. But it's a good, actually analyzing exactly what the parallelism is there is actually pretty good. It's a good puzzle. Maybe we'll do that on the quiz, the take-home problem set we're calling it now, right? We're going to have a take-home problem set. Maybe that's a good one. Yeah, so the idea is you can sync, okay? And in particular, why not compute these, then sync, and then compute these, adding their results into the places where we added these in. Okay? So it is giving, so it's making the program more serial, okay, because I'm putting in a sync. That's going to have an impact on my, that shouldn't have any impact on the work, but it will have an impact on the span. Okay? So we're going to trade it off, and the way we'll do that is by putting essentially a sync in the middle. And since they're adding it in, I don't even have to call the addition routine. Okay? Because it's just going to add it in place. So I spawn off these 4 guys, putting their results into C. Then I spawn off these 4 guys, and they put their results, add their results into C. Is that clear? What the code is? So let's analyze this. Okay? So the work for this is it's order n cubed. It's the same as anything else. We can come up with a recurrence. So it's slightly different from before because I only have an order 1 there, but it doesn't really matter. The answer is order n cubed. The span, okay, now this gets a little trickier. What's the recurrence for the span? So what is that? Twice the span of m of n over 2. That's right. Plus, so basically we have the maximum of these guys, the maximum of these guys, and then this is making those things be in series. So things that are in parallel, I take the max. If it's in series, I have to add them. So I end up with 2 m infinity of n over 2 plus order 1. Does that make sense? Okay, good. So let's solve that recurrence. What's the answer to that one? That's order n. Which case is it? I never know what the cases are. I get, it's like I know 2, but 1 and 3, it's like, okay, they're the same thing. It's just which side is in. So I never remember what the number is. But anyway, case 1, yes, there we go, case 1. Okay. It's the one where this thing is bigger. So that's order n. Right? Good. Okay, so then the work is n cubed. The span is order n. The parallelism is order n squared. So for 1,000 by 1,000 matrices, I get parallelism on the order of 1,000,000. Instead of before, I had parallelism on the order of 10 million. Okay? So this turns out way better code than the previous one because it avoids the temporary. Okay? And therefore runs, you get a constant factor improvement for that. And it's still, on 12 cores is going to run, pretty fast. Okay? And in practice, this is a much better way to do it. The actual best code that I know for doing this essentially does divide and conquer in only 1 dimension at a time. So basically, it looks to see what's the long dimension, and whatever the long dimension is, it slices it in half and then recurses, and just does that as a binary thing. And it basically is the same work, except it's a little bit more tricky to analyze. Okay, let's see. Let me quick do merge sort. Okay, so merge sort. There's merging 2 sorted arrays. We saw this before. It looks, if I spend all this time doing animations, I might as well get my mileage out of it. Okay, there we go. So we merge. That's basically what this code does. Order n time to merge. Okay, so here's merge sort. So what I'll do in merge sort is the same thing I normally do, except that I'll make the merges run in parallel. Okay? So basically, not the merges, I'll make the recursive routines go in parallel. So when I do that, it basically divide and conquers down, and then it sort of does this to merge things together. Okay? So we sort of saw this before. Except now, I've got this fact that I can sort 2 things in parallel rather than sorting them serially. So let's take a look at the work. What's the work of merge sort? We know that. N log n, right? 2t of n over 2 plus order n. So that's order n log n. Okay, the span is what? What's the recurrence of the span? So So we're going to take the maximum of these two guys. So we only have one term that involves t infinity. And then the merge costs us order n. So we get this recurrence. Okay? So that says that the solution is order n. So therefore, the work is n log n. The span is order n. And so the parallelism is order log n. Puny. Okay? Puny parallelism. Log n is like, yeah, you can run it, and it'll work fine on a few cores, but it's not going to be something that generally will scale and give you a lot of parallelism. Okay? So it's pretty clear from this that the bottleneck, where's all the span going to? It's going to that merge. Okay? So when you understand that that's the structure of it, now you say if you want to get parallelism, you got to go after the merge. So here's how we parallelize the merge. So we're going to look at merging of two arrays that are of possibly different length. So one we'll call A and one we'll call B, with NA and NB elements. And let me assume without loss of generality that NA is greater than or equal to NB, because otherwise I can just switch the roles of A and B. So the way that I'm going to do it is I'm going to find the middle element of A. These are sorted arrays that I'm going to merge. Okay? I find the middle element of A. So these guys are all less than or equal to A of MA, and these are all greater than or equal to. And now I binary search and find out where that middle element would fall in the array B. Okay, so that cost me log n time to binary search. Remember binary search? Okay. Okay. Then what I'm going to do is recursively merge these guys, because these are sorted and less than or equal to MA. Recursively merge those and put this guy in the middle. Okay? So when I do that, the key question when we analyze it turns out the work is going to basically be the same, but the key thing is going to be what happens to the span. And the idea here is that the total number of elements in the larger of these two things is going to be at most what? Another way of looking at it is in the smaller partition, the number of elements, if n is the total number of elements, the smaller partition has how many elements at least relative to n? No matter where this binary search finds itself. So the worst case is sort of going to come when this guy is like at one end or the other. Right? And then the point is that because A is the larger array, at least a quarter of the elements will still be in the smaller partition. Okay? Of all the elements here, at least a quarter will be in the smaller partition, which will occur when B is equal in size to A. Okay? So the number in the larger of the recursive merges, it's at most 3/4 n. Sound good? That's the main key idea behind this. So here's the parallel merge. Basically, you do binary search. You spawn then the two merges. So here's one merge, and here's the other merge, and then you sync. So that's the code for doing the parallel merge. And now you want to incorporate that parallel merge into the parallel merge sort. So of course you coarsen the base cases for efficiency. Okay. So let's analyze the span of this. So the span is basically then the span of something of 3/4, at most 3/4 the size, plus the log n for the binary search. So the span of parallel merge is therefore order log squared n. Okay, because the important thing is I'm whacking off a constant fraction here every time. So I get log squared n as the span, and the work I get this hairy recurrence. That it's t of alpha n plus t1 of 1 minus alpha n plus log n, where alpha falls in this range. Okay, this is what's called, this does not satisfy the master theorem. Okay, you can actually do this pretty easily with a recursion tree, but the way to verify it is, we call this technically a hairy recurrence. That's the technical term for it. Okay, so it turns out this has order n, just like ordinary merge. Okay, order n time. And you can use the substitution method, and I won't drag you through it, but you can look at it in the notes. Okay. And this should be very familiar to you as having all A6006, right? Otherwise you wouldn't be here, right? Okay, so the parallelism of the parallel merge is something like n over log squared n. Okay, the work is, so that's much better than having an order n bound. And now we can plug it into merge sort. So the work is going to be the same as before because I just have the work of the merge, which is still order n. So the work is order n log n, once again pulling out the master theorem. And then the span is n over 2 plus log n, because I'm basically, I have the span of a problem of half the size plus the work, the span that I need to merge things. That's order log squared n. So this one I want to pause on for a moment. People get this recurrence? Okay, because this is the span of the merge. And so what I end up with is I get, another log cubed n. Okay, and so the total parallelism is n over log squared n. And this is actually quite a practical thing to implement, okay, to get the n over log squared n parallelism versus just a log n parallelism. We're not going to do Tableau construction. You can read that. That's on the notes that are online, but you should read through that part of it. It's got some nice animations, which you don't get to see. Okay. This is like when you do longest common subsequence and stuff like that, how you would solve that type of problem in parallel. Okay, great.